And as we're going through, if any questions occur to you or you would like anything clarified, do feel free to ask. Yeah, and then if there's still time left over, we can go back and look at some more exercises from the book and so on. Some more questions. Okay. So we were in the middle of answering question 2, which we've given definitions of subgroup and order. We've done this thing on the order of elements of the direct product of 2 finite groups, 2 groups. We did part C, which was an investigation of cyclic groups and proving that every subgroup of a cyclic group is cyclic. We did that by focusing on this model of the cyclic group of order n using multiplicative notation. So this is seen, the cyclic group of order n is the group generated by a generator A, where the group just consists of all the powers of A between A to the 0, so the identity up to A to the power of n minus 1. So part D then takes us into looking at the specific example of a relatively a group of medium size, the dihedral group D15. First paragraph here just summarizes the description of the dihedral group D15. So this is going to be the group of regular symmetries of a regular 15 gone. I'm not going to attempt to draw 15 gone, but it is based on the circle, and it's got 15 sides. 15 right, and there's a basic rotation R there, which is R rotation and S a reflection. You can think of R as being the reflection by R as being the rotation by 2 pi over n radians anti-clockwise. And it also has a single reflection S. Now, if this is a 15 gone, 15 is odd. So the reflection axes are all going through vertex, through the middle, and then through the midpoint of a side opposite the vertex. So S will be reflection one of these. And then the relations, or the kind of key pieces of information about these generators we need, is that R is of order n, because it's n to the full term, so you do it n times, you get the identity. S is order 2, so it's a reflection. And the way S and R commute with each other, if these are the 2 generators, we need to know something about how they commute with each other, and they have this kind of universal principle about reflections and rotations, where the center point of the rotation is a point on the reflection axis. It's always true that S after R is equal to R inverse after S. And then it tells us the 2n elements of Dn can be expressed in this standard form. So the elements of the dihedral group can be written as R to the I Sj, where the possibilities for I are any exponent between 0 and n minus 1, and j any value between any value either 0 or 1. So that means you either have R to the I times S, or you have R to the I. The only options on the exponent j are 0 or 1. Now the question here is, consider the dihedral group D15. Just describe all the subgroups of D15. So and decide if each one is cyclic or not. There's a bit of guidance here for what we're kind of looking for. You do not have to prove that each one is a subgroup, but you should provide sufficient explanation to show you understand how the criteria for a subgroup apply to each one. So not necessarily itty-bitty proofs about all the different properties, but maybe some more of a narration or an explanation. But in terms of describing the subgroups, we will want to describe exactly how many subgroups there are, and point out exactly what the elements of the various subgroups are. Okay. So I guess, so from the description, I would say we should first of all write out, reel out the elements of D15. And it will help just to see them all in front of us for when we're going to start forming subgroups. And that. You've got the, well, just turn up these slides. You've got the question in front of you. Yeah. So the elements, well, it's going to consist of the identity, E. It's going to have the rotation R, the rotation R squared, the rotation R cubed. Well, not write them all out, all the way up to R13 and then R14. Okay. So this is the first. D15 has these 15 elements. So there's 15 here that I've listed. The identity element kind of qualifies as a rotation as well. Rotation order 1. So that's half of the elements, these 15 the elements, and according to the description, the other half of them are the 15 reflections, which are S, RS, R squared S, R cubed S, and so on, all the way up as far as R13S, and then lastly R14S. Okay, in each of those compositions, think back to that sketch drawn on the board here, all of the other axes, all of the other axes are equal to these various expressions, Ri to R to the power I after S. Okay, so this is a group of 30 elements, and it's going to have plenty of subgroups, so we want to list them all. There's two kind of easy subgroups to get out of the way to begin with, which would be the trivial subgroup and the whole group itself. You know, because they aren't kind of really proper subgroups as such. So we should probably describe them first of all. And remember, the question says decide if each one is cyclic. Well, if we're going to be judging, in order to argue about cyclic subgroups later on, we should say what order each element has. So we know already that the identity always has order 1, because remember the order, see things like order and subgroup we defined in 2 part A. The order of the element is the smallest strictly positive integer, such that that group element to that integer power is equal to the identity. So clearly e to the 1 is equal to the identity. So the identity is order 1. The basic rotation R has order 15. And all the other any other rotation, what's the order of R to the power J? I mean, we could go through each one separately and say what order it has, but there is a formula, there is a kind of formulaic way of stating what the order of R to the J is. It's going to be, see, if you look at something like R cubed, when you start taking powers of R cubed, you'll have R cubed When you square it, you'll have R6. When you cube it, you'll have R9. When you raise it to the power 4, you'll have R12. You raise it to the power of 5, you get R15, which is, of course, the identity. So that means that R cubed just has order 5. And it's quite easy to understand where that 5 comes from. It comes from 15 divided by 3. So whenever the j is a divisor of 15, the order of that element, r to the power j, will be 15 divided by j. But what happens when the j is not a divisor of 15? Well, the general pattern is that the order is going to be 15 divided by d, where d is equal to the greatest common divisor of 15 and j. So this will always be an integer because I'm dividing 15 by one of its divisors, d. In the case where j is a divisor of 15, like the case j equals 3 we just thought about, then GCD between 15 and 3 is 5, so d is 5. No, the GCD between 15 and 3 is 3, so d is 3, so 15 divided by 3 gives you 5. But it's for other numbers like, say, r equals 6. So the greatest common divisor between 6 and 15 is, again, 3. So r to the 6 should have power 5 as well. You can test that. E.g., according to this, the order of r to the 6 must be 5. And if you look at that, well, r to the 6 to the 0 is clearly the identity. R to the 6 to the 1 is clearly r to the 6. R to the 6 squared will be r to the 12. R to the 6 cubed will be r to the 18. But you got to reduce that exponent modulo 15. So r to the 15 is the identity, so that's equal to r to the 3. And finally, r to the power r6 to the power of 4 will be r to the 24. Reducing that modulo 15, that gives you r to the power 9. And if you try and do it one more, r to the 6 to the power 5, you get r to the 30, which is, of course, e. So that's the power of r to the 15, r to the 15 squared. So you've got this element r6 to the power 0, 1, 2, 3, 4, but when you raise it to the power 5, you're back to the identity. So that means that has order 5. Okay. So this was one of the results we proved in the course. So not that you'd be able to remember the reference to it in an exam, of course, but just for revision purposes, this will be back in the Cyclic Subgroups chapter. But it is a fact that I expect you to know. And just get the reference to it. The theorem 4.13. Theorem 4.13. Okay, is that okay? Any questions about that? Yeah. Not that you'd have to go through that, I think, go through that example in your exam answer. I'd say just stating that clearly would be enough. That's just to illustrate what's going on. Okay, we're in the middle of listing the orders of the elements, so we've done all the rotations. So the only other things then are to talk about the reflections. But of course, the order of any reflection is always 2, yeah, because these are all reflections. Okay, so now we know, and we've said what the order of each element is. That'll be important for arguing about whether or not the various subgroups are cyclic or not. So we start to list the subgroups. And so firstly,
there exists the trivial subgroup E, the subgroup just consisting of E, and the whole group. It's the whole group, the whole group itself, the whole group D15 itself, which is also a subgroup. Now, the trivial subgroup is clearly cyclic. And it's only got one element in it, so clearly that element is it generates it. The cyclic the trivial subgroup is cyclic because it's generated by the identity. Is the whole group D15 cyclic? So remember, the definition of cyclic is it has a generator. Can any of these 30 elements, okay, D15 contains them all, can any of them act as a generator? It's a single generator for the whole group. Well, you see, if it did act as a single generator for the whole group, taking powers of that element would have to build all 30 of the elements. But we've just described all the orders of all the individual elements. We either see things of order 1, order 2, or order 15 over D, where D is a divisor of 15. Yeah. So the maximum possible order that something has in D15 is 15 itself. So you can never generate all 30 elements from something. Okay. So you just described that. D15 is not cyclic, as all elements, every element has order less than or equal to 15. See above. Okay, it makes sense to deal with those two subgroups, first of all, because they will always be present, the trivial subgroup and the whole group itself. Now we should go on to consider genuine subgroups as such. Now, we've got there's a few of them, so we want to describe them systematically in some ways, and make sure we don't miss out any. Okay. Basically, the subgroups of the dihedral group they come in two types. Those subgroups which contain some reflections, and those subgroups which don't contain any reflections. It's basically in those two types. So it's simplest if we leave out the reflections for the moment, and just consider rotational subgroups. Okay. And the subgroup R, consisting of all the rotations, is clearly a subgroup. So R is the E, R squared, all the way up as far as R14. It's clearly a subgroup as, what's the easiest way of kind of convincing the reader that you appreciate what's a subgroup, because, and we also deal with the cyclic nature. You can see straight away that it's cyclic and it's generated by R. Because by definition, it clearly consists of all the powers of R. So it is cyclic and generated by R. You okay with that? I mean, it's kind of obvious it's generated by R. It might also be good if you could give all the other generators of it, because it can also be generated by lots of other elements. And you're basically coming back to this thing here. So any power of R to the J, where the J is co-prime to 15, or the greatest common divisor of 15, and J is going to be 1. So the D is 1, so that element will have order 15, so therefore it must generate all the 15 rotations. And in fact also generated by, so 15 is 3 by 5, so basically all other powers are squared, not R3, R4, not R5, not R6, R7, R8, not R9, not R10, R to the power 11, not R12, R to the power 13, and R to the power 14. Any of those also generated. Yeah. So that's a subgroup, that's cyclic. Then we also have subgroups of R. Yeah, because any subgroup of R will in turn be a subgroup of D15. But now this puts us straight back into the situation of part C, doesn't it? Cyclic subgroup of order n, written multiplicatively in terms of a generator array. Well, that's exactly what we've got here with R15. It's the same as C15. Yeah. So we can use what we described there. And there we proved that every subgroup of the cyclic group was cyclic because it was generated by a to the power k, where k was the smallest positive integer, such that a to the k was in H. So we also have subgroups of R, which is described in part C, since R is equal to C15, if you like, or isomorphic to C15, maybe say. And these are the cyclic subgroups. Each of these are cyclic because we proved that every subgroup of R is going to be cyclic. We proved that in part C. These are the cyclic subgroups. So which ones are there? Well, they won't be generated by any of these elements because we've already indicated that those can also play the role as generators of R itself. So it'll be the other ones. It'll be the ones that are expressed as R to some power where that power is a divisor of 15. Okay? So you'll have R cubed. That generates E R cubed, R6, R9, and R12. That's a cyclic subgroup of order 5. And indeed, any of those elements can be taken as generators. Yeah. So it's a group of order 5, which is a group of prime order, where every element is going to have order 5. Every non-identity element is going to have order 5. Yeah. Because the order of an element has to divide the order of the group from the Lagrange's theorem. So there's that one. Then there's also R5, which is the identity R to the power 5, R to the power 10. That's it. I mean, the next one you're tempted to write down is R to the power 15, but that's already there. That's the identity. Okay. So that's the cyclic subgroup of order 3. And there aren't any other ones. Okay. So R is the cyclic group of order 15, so it's got subgroups of order 5 and 3. But no other ones. And only one subgroup of order 5 and only one subgroup of order 3. Okay. So in fact, we've got all 15 elements, all of the 15 rotational elements again on the page there. In terms of these elements, you've got E, R5, R10, R cubed, R6, R9, R12. Those are all generators for their respective subgroups that they're in. And then all of these ones, these are all, of course, all the rotations are in R, and all of these ones are generators for R. So those are all the subgroups that don't have any reflections. Okay. So R and its subgroup, R and its subgroups, along with the trivial subgroup E, are all the subgroups without reflections. So we then go on to describe the subgroups that do contain reflections. What's the simplest subgroup that contains a reflection? Do you think?
Would it just be S?
Just be.
S.
So what else is in the subgroup?
Oh,
So yeah, you're right. Just S. So you take one reflection and just consider the subgroup generated by that. Because every reflection is order 2, so you're just looking at S and E.
Yeah.
Yeah. So you got S to the power 0, which is E. S to the power 1, which is S. S squared. Well, that's back to E again.
Yeah.
So you got the cyclic subgroup generated by S. Now S is just our one special named reflection. But then all the other reflections are just combinations of some power of R after S. Yeah. And so they're all going to act the same way. Okay. So we have 15 subgroups of order 2. And they are the cyclic subgroup generated by R to the JS, which consists of the identity and the reflection R to the JS. And this is for each J between 0 and 14. So you can describe them just in one line, rather than write a separate statement for each one, because really they're all the same. They're just one of the reflections and the cyclic subgroup is generated by it. So the case of S itself is just where you've got J equals 0, R to the power 0 is the identity, so it's just ES as well. So 15 subgroups of order 2, all of them cyclic. Cyclic by definition. So then you're going to have, so those are like purely reflectional subgroups. But then you think about what happens when you start to mix rotations and reflections. Now we can make use of some of the stuff we've already built up there. Remember, and one part of the definition of subgroups is that subgroups are closed under the operation. So for instance, if any subgroup which we've yet to write down, if it contained R5 ever, it would have to contain all of this. It would have to contain R5 and R10 as well, because R10 is R5 squared. Similarly, if any subgroup we write down contains R9, it's going to have to contain all these rotations at least, because these are all just powers of R9. Remember, any of these elements can be taken as generators of this. So any subgroup we've yet to write down which mixes reflections and rotations, it's going to have these, one of these rotational ones as a subgroup in it as well. So in that way, we can kind of use those ones as the building blocks. And in a funny way, you can just, you could take your reflection S and toss it into one of these, so to speak. I'll show you what I mean. Other subgroups which mix rotations, because those are the only other ones that we haven't talked about yet, which mix rotations and reflections, can be any of, well, okay, I'm going to start calling these H. So we got H1. So here, let's take the simplest rotational subgroup we have, and let's throw the reflection S into it. So it'll consist of that rotational subgroup. And if we throw the S in, it'll consist of S. But then immediately by closure, it will have to consist of R to the 5S and R to the 10S. But it won't have to consist of, it won't have to contain any other element, because we've already got closure and presence of inverses satisfied there. We already had closure and presence of inverses satisfied here. Each reflection is its own inverse. So the only other thing we have to worry about is closure here. And notice that if you take any, like if you take an RJS and compose it with an RKS, and then we're going back to one of the relations contained in the description at the start. This is going to be R to the J, R to the minus K S squared SS. Because in the question, we have this fundamental rotation that if you've got an S and an R, you can move an R to the left of an S, but it turns into an R inverse. You see that? So doing that repeatedly, you move all of these K R's to the left of that S there, each one becomes an inverse, R inverse. So you'll have R inverse to the power K, or in other words, R to the power minus K. Then you got the two S's beside each other. So that is just the identity. So you've just got R to the J minus K. But of course, whenever we do, whenever we add exponents there, and those are, we're always interpreting the answer modulo 15, aren't we? Because R to the 15 is the identity. And the S squared is the identity, of course, so that it disappears. So if you combine any of these, if you take the product of any of these reflections, you're always going to get another rotation where you either add or subtract the 5 and the 10, or the 0, which is the exponent of the R here, and interpret the result modulo 15. But whatever R is going to pop out at the bottom there, you've already got. Okay. So from this we can see H1 is closed under the operation, and contains all inverses. So it is a subgroup. Is it cyclic? What would you say to that? Is it cyclic? Well, so that's the question, is, are any of these 6 elements a generator for? So the subgroup has order 6. So if it has a generator, it has to be an element of order 6. But we've already described up at the top the orders of every element. These ones have order 2, so reflections. That has order 1, it's not going to be a generator. And R5 and R10 both have order 3. Because GCD with 15 is 5, so 15 divided by 5 is 3. So you've only got elements of order 2, 3, and 1. So there's no generator there. H1 is not cyclic, as all elements have order 1, 2, or 3. So we formed that by taking one of our rotational subgroups and throwing in the reflection S and seeing what came up. So we can throw the reflection S into the other one as well, the other rotational subgroup we had, which is this one of order, that one of order 5. So also H2, which is E, R cubed, R6, R9, R12, S, R cubed S, R6S, R9S, and R12S. That's also going to be a subgroup. This again is a subgroup. What size does this one have? This one has order 1, 2, yeah, order 10. Order 10. We can see closure. It's closed by the argument above, meaning this one about what happens when you compose two different reflections. I mean, it's certainly closed when they're multiplying rotations, and so you only have to worry about what happens when you multiply two different reflections. So you're going to get what you get when you combine the two exponents from the rotations modulo 15, but whichever way you do that, you're going to get one of the rotations that's already there, because we've already ensured that all products of these rotations and their inverses and so on are here, because we have the rotations. And if you compose any rotation with a reflection, you again just get another rotation after S, where the exponent is some combination of exponents we see here on the rotations from modulo 50. But we've already got all of those there. But this is not cyclic, again, and again not cyclic. Again not cyclic, as no element of order 10 here. In fact, there's no element of order 10 in D15 at all. And everything here either has order 2 for the reflections, 1 for the identity, or order 5 for all those rotations. You just see orders 1, 2, 5. And that, I believe, is everything. Where is it? Be careful. Yep, by Lagrange's theorem, any subgroup of D15 has order a divisor of 30. Yeah. 1, 2, 3. 1, 2, 3, 6. 5 is in there. 5. 10, 15, 30. Those are all the only divisors of 30, aren't they? 1, 2, 3, 6, 5, 10, 15, 30. Yeah. And we've seen subgroups of all those sizes. The whole group, D15, the rotational subgroup, R, the group H2 of order 10 we just saw, rotational subgroup of order 5, the rotational subgroup of order 6, the reflectional cyclic subgroups generated by a single reflection, the trivial subgroup, and 6 was that subgroup H1. Yeah. So there are no other ones to find. And so that completes the list. That completes the list of subgroups. Okay, I spent quite a bit of time on that, but you know, I added in a lot of detail there, just kind of revising the topic as well. You might also show, I mean, okay, I wouldn't spend ages explaining it because it's not really asked for in the question, but it'd be good to notice that this is actually isomorphic to D3. And this one is actually isomorphic to D5. And that has some connection to the way that you can inscribe triangles and pentagons within the 15 code in a nice way by making use of the vertices of the 15 cone. Start at a vertex and go to every third vertex after that. You'll trace out a pentagon on 5 sides. Go to every 5th vertex after that one, you'll just trace out the triangle. Yeah. So it's that connection. Okay, so it's just a test. This afternoon we'll have a look at that final question, question 6.